Kate kicks a soccer ball with a mass of 0.548 kilogram. Her foot exerts a lofty 17.4 Newton force upon the ball. This soccer ball accelerates without friction or air resistance for 3.0 meters, then impacts a larger soccer ball with a mass of 1.14 kilogram in an ideal elastic collision. The larger ball then impacts a spring with a spring constant of 56 newtons per meter. How much would the spring compress when impacted?
It is important to remember that when Kate exerts a force on the ball also exerts a 17.4 Newton force on her foot, as stated in Newton's third law. We use Newton's second law, which states that net force equals mass times acceleration to solve for acceleration. We then use the acceleration found and the distance given to find velocity using a kinematic equation. This ball will remain in motion until another outside force is exerted on it, as explained in Newton's first law.
When the two soccer balls collide, an ideal elastic collision occurs. In ideal elastic collisions, both kinetic energy and momentum are conserved. We are using conservation of momentum to calculate the larger soccer ball's velocity after the collision.
Since energy is conserved in an ideal elastic collision, mechanical energy equals potential energy plus kinetic energy, and they should sum to zero. Potential energy of a spring equals 1/2 times the spring constant times the compression of the spring squared, and kinetic energy equals 1/2 times the mass times the velocity of the object squared. We then simplified our equations and plugged in our values to solve for x. After rounding for sig figs, you find that the spring compressed 1.3 meters in the negative direction.